now it should be recording. And yes, it is now recording. And I start. So good morning, everyone. Lecture 3 finite volume method. And this is a method that OpenFOAM is using, finite volume method. So last week we discussed about finite differences, and now we talk about volumes. So as I mentioned last week, on uniform computational grids, these methods commonly boil down to the same method. So finite volume method is mostly needed when you have different elements. So if you divide your computational volume in, let's say, arbitrary polyhedra or stretched or somehow like skewed elements, in that case, finite volume method would be the method that works for that. Finite difference method is typically intended only for uniform and orthogonal grid types when you have rectangular hexahedral elements. Let's, howsoever, first look at one example from a simulation from our publication a few years back. So I talked about convection diffusion equation, which is the main governing equation that we always are looking at. So Navier-Stokes equation is a special case of convection diffusion equation. And let's look at a certain chemical reactor. So here is, at least for me, the animation is blinking a little bit. Maybe the frame rate is too high. But this was a case that we looked a few years back. So it was a chemical reactor. You have a vessel and you have 4 inlets. So these 4 inlets are shown over here. You have gas coming from different parts of the system, from the upper part of this reactor, and then you have outlet. You have outlet in the bottom of the page, and the gas is leaving out from the bottom. There was a certain chemical reactions that are happening inside the thing, and actually this system was used in the atomic layer deposition process, which is a chemical process where different samples are coated. So if you have objects or let's say electronic components, you can put those into this kind of a reactor, and then you bring in certain chemical vapors in different order, and these will create a layer by layer highly conformal coating. So you have different molecules in different order, different gases in different order, and then these will form a solid, very hard layer on these coated samples. So it was a chemical application, but we were doing this in collaboration with the group who looks at these processes more. Here you see the grid. So the computational grid was this kind of like, it doesn't allow me to draw here, but anyways, you have in the upper picture you see that there is different refinement regions. You want to refine where the jets are coming, so you have 4 streams coming. So you need local refinement regions, and then you have a coarser parts of the grid. So it's coarser cells, bigger cells in those parts of the domain where you don't need so high resolution. So you know basically the physical phenomena that you want to solve. You want to solve very well the jets. So if I look at the jet once again, so the jet is where you have the mixing and the shear and the turbulence, and a lot of these small scale vortices that are mixing the gases. So you want to have a good resolution in those parts, and then in other parts, let's see a little bit. And then in some other parts, there is not so much things going on, and you don't have to worry so much about the resolution. Here you see how it's mixing, and then eventually this blue vapor gases. It's blinking a lot on my screen. I don't know what's the reason for that, but apologies for that. Probably the connection or something. And now you see how the blue gas is eventually leaving the reactor. And in this system, you would finally bring other species to the system, and so it kind of, you go blue gas, then you bring, let's say, red gas, blue gas, red gas, and in this subsequent order, you form the chemical coating on the samples. The simulations here were carried out by OpenFOAM. It's OpenFOAM because the geometry is complex, so OpenFOAM is good for this kind of complex geometries, like most engineering applications are complex geometries. Then second order space-time, so second order because we want to have as high accuracy as possible in OpenFOAM. Unfortunately, we cannot go higher really in OpenFOAM with the present discretization scheme. So this is typical in engineering applications. So second order is typically enough. Navier-Stokes equations are solved for the fluid and the convection diffusion equation for the passive scalar. So basically this is modeled as incompressible flow because it's low speed airflow, and passive scalar, so the blue color is actually following the convection diffusion equation. It's blinking too much on my screen. So passive scalar because we assume that the scalar is not interacting with the flow. So the flow is transporting the scalar, the concentration molecules, but the concentration molecules are in such small amounts that they don't really, the velocity field is not kind of seeing those molecules. So that's why it's called passive scalar. This is typically like smoke in a room, cigarette smoke. So it doesn't really, the airflow doesn't too much care about the smoke particles. They are quite dilute and let's say sparsely located. So, but of course, if it becomes very dense, then it's a different case. But under certain approximations, assumptions, you can assume that the smoke is a passive scalar. It is just transported by the wind, but the wind itself doesn't care about if the particles are there or not. Then, yeah, it's also assumed that these are gases, but we assume they are isothermal, temperature is constant, and then its incompressible assumption is typically good. Low Mach number, low speed flow, and this air is essentially it's incompressible that you have in a normal room air conditions, for example. You have small density variations, but those are maybe like 1,000th or something of the average value, so you can neglect that with good accuracy. You have certain Reynolds numbers for this flow, and well, actually the one that you saw was quite high Reynolds number, a few thousand, because it's turbulent. So it was turbulent. We also studied laminar cases. Right. any questions about this case? So this was actually a publication, and I just wanted to show it as an example that you can do different kinds of things with OpenFOAM when you get more advanced. But on this course, we are mostly focusing on some basic cases, simple geometries, laminar flows. Let's now talk about the finite difference method, a short recap. I will actually now show you how you can do this in MATLAB so that it becomes more concrete, because you will need these skills in the final assignment. But maybe it's good to see it in MATLAB, so then you can have a better feeling that how you would actually do this in practice. So 2 recaps. First recap is that we have talked about the continuous equations, Navier-Stokes, the convection diffusion equations. So we always have the same format. We have time derivative of some transported quantity, like the smoke concentration or temperature or something. Then we have a space derivative. The first one is always in the convection term. So remember that we have the velocity is over here. And then we have the diffusivity. Note that this is now the Greek letter nu. It's not V, it's Greek letter nu, and now it's the diffusivity. And the nu has a unit which is meter squared. Meter squared over second. And then we have the diffusion terms, so we have the second derivatives. So now when we discretize this with finite differences, we have these formulas that we discussed last week that come from Taylor series, and next I will show you how you implement this equation in MATLAB. So let's now look at MATLAB. You don't have to do anything yourself. I will solve this equation now in let's say 10 minute in a 10-minute demo or so. Hopefully we manage in 10 minutes. So, and in the final assignment you can also use Python, but here I'm using MATLAB and providing the support in MATLAB. Or any language you can use to solve these. So let's just first of all, I open the MATLAB terminal. Here is what it looks like. I gave you a primer, let's say a few tutorials in the discussion forum in the course homepage, so you can look at the basics. So now I will just show you quickly the main ideas and go more in detail, probably in next lecture. Next lecture I will probably teach you more MATLAB when we do things about matrices. So in MATLAB, I first of all I open an editor. So I'm about to write a short piece of code. So first of all, you can program MATLAB like this. You can declare variables on the screen like this, and these variables are seen on the right column. You see that you have 2 variables. Now you can sum them, and this is one way of working with MATLAB. So you can use it as a calculator. But now what I'm doing is I'm writing a short piece of code, and in this code I'm going to solve the convection diffusion equation. And I'm writing it as a comment. And so let's say that we want to solve, I hope you can see the text, by the way. We want to solve d t dt plus u times dt dx is, I called it nu d squared t dx. So I'm talking about the same equation as over here. First derivative, second derivative, velocity, and then diffusivity. And so first of all, we want to say that we have a one-dimensional something. I will just draw a picture of the initial condition. Let's call it T0 is the initial condition. Let's first of all say that we have a domain x equals, let's say, so we have a domain of length, let's say 1 meter. That's the domain length. That's the x interval. We want to solve from 0 to L. Then we want to say that we put there 100 points. How many grid points? That's the resolution. And now we say that we have an initial condition, which is, let's assume that we take this Gaussian function, a smooth profile in the center of the domain. So it would be this test function, x minus L over 2. And then we need, Gaussian functions have the standard deviation, which is often called sigma. And I write sigma is L over 10. I remember that that's a good value because it nicely fits into the domain. That's the standard deviation, which is the width of the Gaussian pulse. So this you can go to some mathematics books or statistics books to find this function, but it's going to give you the Gauss curve essentially. And now let's just look at the picture, how it looks like. I'll open a new picture. I clear the figure. Here I write always clear all. And I'm just going to draw you a picture of that function. And I have to give it a name. Here is the Gaussian function. Can you see the function?
Yes, we can. Thanks.
Excellent. Excellent. And let's look at the derivative of that function, because when I'm looking at these equations that we have here, we have different derivatives, and we want to simulate that something is evolving in time. So these derivatives are affecting locally how things will behave in time. So if you look at this function, you see that on the left side you have a positive slope, on the right side you have a negative slope. So this will have an impact how the time derivative is behaving, because if you think about that, you put the space derivatives on the right hand side. So basically the signs of these first and second derivatives, they are somehow like impacting like how the time derivative, is the solution going up or is it going down? And let's look at the picture of the derivatives. So how do we calculate the first derivative? So let's first of all say that now we initialize our temperature field. T is T0. That's the initialization of, should we call it temperature? Let's call it temperature. Temperature, it's some scalar. or let's call it concentration. So we would like to calculate dt dx. And this formula is, the discretization, the central difference formula is telling you to take the 2 points around the I point, I plus 1 and I minus 1. And one way to do this is to define that you have, first of all, you have internal indices. This is, let's say, probably hard to understand first, but I will clarify next week. So you have the right side indices, you have left side indices, and then we have periodic boundary conditions. So you just have to hold on and look at the result. We have plenty of time to clarify everything I'm doing. This would be the internal indices. So this would be the numbers 1, 2, 3, all the way until it would be a list, a vector of the numbers. So let's run it. Okay. And we would like to now calculate this derivative. It should become completely obvious now. 2 times dx, and it still doesn't work. You see, it doesn't recognize what is delta x. And we have to give a delta x. So this is just the central difference 2 formula. So delta x is L divided by the width of the domain. This would be grid spacing dx. And let's look at the picture of the derivative. Let's write. Right, does it make sense? To me, it makes sense that if we look at the first derivative, dt dx, you see we have dt dx over here. Here I'm using central difference formula to calculate it. I did a small trick in between, but trust me that this goes right. Look at this. Makes sense. You have positive value of derivative now on the left side, and then you have negative value on the right side. So of course, this is how the derivative of this function should behave. It's going up, positive derivative, it's going down, it's negative derivative. And let's at the same time solve for the second derivative. You see, d second dx squared is, so now we use the second order central difference formula. 2 times t. So this would be central difference for the second derivative. So remember, we have this right side index, then minus 2 times the internal index, and then the left side index, and dx squared. And this is exactly the formula that I'm giving on the lecture slides. So the second derivative is seen over here. So the formula has this 1, minus 2, and 1 coefficients. Very famous formula. And let's look at the picture of the second derivative. And I think next week you do this yourself and in the final assignment. Okay, so this is a bit more complicated. But anyways, you see that the second derivative, it should look more complicated, right? So now we should have positive values, then it's turning negative at some point, negative, 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 then it's turning positive again. It's matching what we have over here. So the second derivative is here, first derivative is here. So the shape is more complex. And let's now actually solve the convection diffusion equation. So we see that if we can write an Euler method plus central difference 2 to solve convection equation. Let's write a time loop over, let's simulate 1000 time steps. And what do we want to do? We want to, first of all, we want to calculate. So I'm going to write a time loop. And first of all, I want to calculate what those derivatives are, right? So I don't know, when I'm looking at this equation over here, I don't know what the derivatives are, but numerically I know my data. So I know the numerical solution in n grid points. So I have, let's say, 100 numbers in the list, in the vector. And using these numbers, these 100 numbers, I want to calculate the first and the second derivative. And I'm doing it over here. After that, I want to take the known terms, so the space derivatives to the right side. So take those to the right side of the equation, and I want to use Euler method to calculate the delta t. So you see what I'm doing here. I say that change in temperature or concentration equals the time step times minus u times dt dx plus nu times d. And you remember that I still haven't defined what is velocity. Let's say that we have a wind from left to right plus 1 meters per second. U is the wind velocity. Then we have nu, which is the, let's write 1, that would be the diffusivity. And then we still have a time step. Let's write 0.0001. This would be change of concentration in each point. And then finally we update. And does it work? I think I never made it work on the first time. Always need some debugging, but if we are lucky, it could work. Let's write here a small picture number 4 that line 35, missing characters. And you see now this is a very good demonstration of a numerical instability. The solution kind of exploded here. Let's have it another time. So do you see what is happening? Numerics didn't work. Very good demonstration. Goes completely nuts here. So let's figure out the problem. The problem is that the time step and the Courant number are too high. So if you calculate Courant number u times dt over dx, okay, that would be Courant number 1. That's suspicious because usually these schemes you have to have like much less than 1 Courant number to have a physically meaningful solution. Let's try a smaller time step. Let's write dt is 0.001. Still having trouble. And what is the problem now? You see, that's the time step, that's the Courant number. Courant number is 0.1. That should, from the velocity viewpoint, that makes sense. But if you look at diffusivity, diffuse Courant number, the CFL number, that's 10. Too high, way too high. Check the previous lecture slides to understand what is CFL and CO. So you need to have a small enough time step to not convect or diffuse the solution over too long distance within a time step. That's the reason why we need a small time step. Let's make diffusivity just smaller. Let's make it 0.01. That should fix the problem. So here we are now looking at the convecting pulse. And what is very important to note that it's not only convecting, but it's also diffusing. So you see that the peak value is coming down. Maybe I write there. Let's write there. So I think that this now should give you a pretty good feeling how convection and diffusion act at the same time. So while the convection, the wind is blowing from left to right, that's transporting, that's shifting the center of the pulse from left to right. I hope you, by the way, see it the same direction as I'm seeing it, because sometimes the image is mirror imaged. So my left to right can be your right to left, but I see it going from left to right. And anyways, that's what I'm seeing here. And you see that convection is shifting and shifting and shifting. But you see at the same time what the diffusion is doing. The amplitude is coming down. And now it went once around the domain. I believe it went once. And you also see what the periodic boundary condition means. So periodic boundary condition means that it's something that we often use in numerical testing mostly. That what goes from the right end comes back from the left end. So this is to make the domain shorter. And how do I know that this was a conservation law. So remember that convection diffusion equation is a conservation equation, conservation law. So when we have this kind of equation, it's telling us that things are transported and they are diffusing by molecular diffusion or some other diffusion. But the physics is that this represents a conservation law. And the conservation law means is that whatever the stuff is that's being moved, whether it's smoke particles, number of smoke particles, or whether it's thermal energy or chemical species, unless we have chemical reactions or nuclear reactions, things should be conserved when we solve for this particular equation. And what does this mean? So if we assume that this was a concentration of smoke particles, so let's assume that this was a smoke cloud, smoke aerosols that were transported by wind. And let's say that this diffusion represented some kind of, let's say, small scale turbulence or something that was a little bit, let's say, making the cloud a little bit dispersed, but just a little bit. So there was a small diffusing and a mixing, like a random diffusion effect, but there was also the transport by the wind in this problem. And let's say that these were smoke particles. This was smoke concentration profile in the x-axis in time, along x-axis in time. How do we know that the number of smoke particles was conserved? Anybody? How do we know that this was the conservation law? What kind of test? What kind of test should I make to prove it?
For example, graphically, if you integrate the area of the curve, it should stay the same.
Exactly. The area of the curve should stay the same. And how does this translate in numerics? We have concentration values, let's say 0.6, 0.5, different 100 different values in different points. So how would you test this in MATLAB? I should like plot something probably on the screen. How do I do it? How do I integrate numerically? That's the question.
Well, you take a sum along the x-axis of the 100 points.
Exactly. Precisely. I could multiply it with delta x, but that doesn't really. That's just a constant that multiplies everything. So it doesn't matter. So I'm actually now printing it on the screen. So what I would like to see is that this code should be like printing on the screen on each time step the sum of essentially the integral of the temperature or the species, the concentration. So I'm just writing this sum t over here, and let's run it. Let's see what the okay, you see it over here. It's not clearly visible, but because you don't see this blinking, but you see it's printing every time. On every time step, this is what it prints out. 24.8, 24.8, 24.8, 24.8. The same number each time step. And what this means is that nothing is disappearing from this system. The shape is diffusing, the amplitude is coming down, but it's diffusing more, it's taking a broader area, and it's transported, but nothing is disappearing. The sum is the same. And that's the whole point here. This is a conservation law, and this numerics is conserving the stuff that we are like transporting with the equation. any question at this point? I will kind of get back to this one next week as well.
Yeah.
Yep, just you can start.
Well, I had a question. If, for example, in this case, we are considering the temperature, how this conservation could be basically interpreted. I mean, in terms of concentration of particles, I can understand it, but how about the temperature?
Then it would be thermal energy. So basically you have, let's say, specific heat times temperature, and then you multiply with density, and if you assume density is constant, then that would be conservation of thermal energy.
Okay, yeah, thanks.
Remember that it's a good one because we have two types of energy. We have kinetic energy of gases and fluids, and then we have thermal energy. And if I'm looking at, for example, this problem on the first page, so this is the lecture under lecture 4, actually, the picture, the colorful picture where you have a channel with hot walls. So incompressible, let's say, water in a small channel, in a 2D channel, and the water is heating. So we are looking at the color scale is the temperature of the water. So in that case, that would be an example of conservation of thermal energy. So temperature is convected and diffused according to exactly the equation that I just solved. But now it's in 2D, of course, in this picture. But the main idea is the same. Temperature is heating the water, and this water is transporting this temperature and the heated water. So basically, this is the thermal energy transport problem.
Yeah, thanks. Very well explained. And can I ask the other question? If you go back to your MATLAB code, I had a question regarding, let's say, I guess that was a central difference, let's say, method that you use for differential equation, right?
Yes.
So yeah, just wanted to confirm it. I guess I can read it through from MATLAB help about the central differences method, right? And the way that you formulated the, let's say, how to say your differential equation.
This one or?
I mean this dt and the third equation. I guess it's yeah. So could you just explain how you formulate this equation? I guess it's the same as what is in the lecture, but probably some different arrangement, right?
Yes. So first of all, okay, this first derivative and then the second derivative of the function are over here. So and then you have minus u over here. That's u is the wind velocity. And the minus comes from that we take the terms to the right side. And if we look at, I hope that I'm answering the right question over here, but I'm basically looking over here this transport equation for a scalar, and I take the velocity terms, the known terms to the right side of the equation, so that I have time derivative on the left side and all the space derivatives on the right side. That's what I'm doing. So the minus sign is coming from there. And then I want to find write this so that this is on the left side, the time derivative. And then I multiply with time step. So basically the time derivative is d phi over delta t. And now this delta phi in the nominator is the change in time in a given point. So that would be like, we can say that in a given index point I on a given, this is not collaborating with me. It's not collaborating very well. But actually the equation below shows it even better. So when we write it in this form, so we have delta phi over here, and when we multiply with the time step to the right side, then we actually got in every single point, in 100 points, we got the change of that quantity in every single grid point. And then we just add it to the previous value. That's what I'm doing. Is this making sense? Is this complicated?
Yeah, that was exactly my question. And if I'm not mistaken, in this case, let's say delta phi is our temperature for the example that you just saw.
That's the dt that I wrote. Yes.
All right. Yeah. Thanks a lot.
Yes.
Question about
yeah.
the
Go ahead.
code. When you define a bit further up, when you define the indexes, or when the left-hand side and the right-hand side, it's a more MATLAB specific question, but how did you define it in such a way that if you have the first index and look for the first index -1, you don't crash it because it cannot find the one before it?
And that's what I'm doing over here, is that this is the, you see that I first of all take the -1, and then I this is the trick.
You define it as the highest point again.
Yeah, I say that on the first index, the left side is, there's nothing on the left side, but I say that it's actually the right side. So that's the periodic boundary condition. So I'm, let's say, cheating a little bit over here.
Okay, that's clear.
Yeah. Right end, I have the same trick, that I do a periodic boundary condition, so that I say that what's on the right side of the last point is, there's nothing, but I say that it's the first one. So then it's looping in the loop, the solution. Yeah, good questions. Anything else? Perhaps to summarize, I think that this is so simple way to solve differential equations, and if you would extend this to 2D, it would be straightforward. You would just calculate more of these derivatives, the y derivatives, and you would in exactly the same way you would take those into account over here. Very easy. A few lines of code, and maybe let's say that 20 years ago people were actually solving these manually, but that is very difficult, and even to look at the manual picture, you will have very complex solutions, and well, maybe not in this one, but maybe in some more complex cases, you get very complex solutions, and you still need computer to look at the solution. So that's the benefit of computers. We can do pretty quickly things nowadays, and understandably as well, I think, my opinion. Any more questions? Maybe we could have a, let's say, 2-minute break and continue after that. If you want to take a short break, I will just start right away, get a glass of water, and then return here to the finite volume method. See you soon. Okay, here we are back. Someone may be having a microphone on. I hear some noise in the background, but it's not too bad. Anyways, let's start and continue. Okay, the purpose over here is that maybe I will skip this one, but if you do solve Navier-Stokes equation, the idea can be like very similar to what I just showed in the 1D example, that you need to find partial derivatives, different partial derivatives using central difference or respective formulas. Need to discretize time somehow, and in the end you want to find the solution on the next time step. So essentially what you want to find is delta u, change in velocity, in the same way as we found dt or d phi in the previous example. So that's numerical schemes. Maybe I could start with this one. So let's actually look at this definition first. So if you calculate average of a function in 1D over a small interval, this is the definition of average of a function. So you integrate over that small interval and you divide with the length of that interval. So that's basically like a mathematics definition of a function, average of a function. So what does this mean? You take the interval delta x and you integrate from x minus to x plus, and let's say that you have some function like d phi dx. You integrate that function over the interval. It just becomes a substitution in the endpoints of the interval to that underlying function phi. So it's just the function at the endpoint minus the function at the starting point. So basically the values of the integral function at the endpoints of the interval, those will determine the output of the integral. Like just to back up and fundamental things. So this one you know very well, and actually integration is actually a simple version. So if we think about the 1D example that I have over here, that's actually a simple version of the Gauss theorem. So Gauss theorem is extension of 1D integration to 2D or 3D. So here we had it 1D. If we have it 2D or 3D, we would call it the Gauss theorem. 1D, that would be probably most commonly called just integration. The equation that we just solved using MATLAB by finite differences. So the common transport equation we always solve is this one, convection diffusion equation. And let's now use volume averaging or averaging over a small interval. So basically let's use this definition over here, definition of average of a function. This definition and use it over here. So we are integrating. You see that we have this integrand over here. It's appearing 3 times. So we are just integrating this equation over a small interval, like locally. And over here, this is the definition of these endpoints. We integrate from x minus to x plus. So now we assume that our grid is located in these, or our solution is defined in these cell centroids. So cell centroids are these blue points. And we integrate over the cell faces, x minus and x plus. So now these x minus and x plus are like in between 2 cell centers. So you have cell center, cell center, cell center, and then you have the faces, which are center is here and the faces are here of the cell. And when we do this integration, we see that this simplifies. So we see that actually we can write this, we can swap the order of integration. So this time derivative comes out. Over here, we assume now that velocity is even constant. So actually we can integrate it. So actually now we have this only phi, the integral disappears. So we have now only a substitution over here. And here is the same story. We integrate once, so we only have the first derivative anymore. And over here we have the substitution. Integration completed and local averaging of the solution. So this is basically now the starting point how the finite volume method is derived. Integrate over a control volume or control interval. So now we just define a little bit simplify. We say that okay, these two are approximately equal. So this allows us to say that okay, the time derivative is as it was. Then the convection term, you can estimate this using the endpoint values of the data. Here we have x plus and x minus. And now the length of the interval was delta x, and that delta x comes from over here. And finally, the diffusion term. So we are now approximating the diffusion term. Diffusion term, you have the derivatives at the endpoints. And yeah, this same delta x, which is dividing here all the time. Just elaborating the 3 terms on the previous slides over here, from here to here. And now the question is that how do we define these numbers? And the answer is that we need to interpolate. We need to interpolate quantity the cell phase. So you remember the thing is that we now assume that those blue points are the solution points. That's where we know the solution from the previous time step. That's where we knew it from in the MATLAB code as well. We assume that we know the solution in these blue points, and we want to find the solution in those brown cell faces. And we need to interpolate the solution in these points, and we need to interpolate the gradients in those points as well. So how do we get those? We can simply linearly interpolate. So you take the average of the neighbor points, I plus 1 and I, the average of those 2 points divided by 2. That would be a linear interpolation. The same story here, if we have x minus, then we have to have xi and xi minus 1. And for the gradients on the cell faces, you can use central difference for 2 adjacent points. Here the same story. And when you plug those together, you will find interesting things. We have started with this integral locally averaged convection diffusion equation integrated over this small interval divided with the interval length. And we kind of find this semi-discrete form. So when you basically plug in this slide and this slide, you see that you actually recover terms that look like this, and you see that this is actually the finite difference, central difference discretization. Almost like magic happened over here. So we didn't even use a definition of Taylor series or anything. We just volume averaged over small cell, used the integration law, the Gauss theorem in 1D, and then we get the same equations as in the finite difference discretization. So in simple words, this is what the finite volume method is about. You need to discretize time as well. In the simplest way, you could use the explicit Euler method. That's, by the way, the worst method, but I'm using it for demonstration purposes because it's the easiest method. So nobody would never ever use in practice this kind of very simple formula for time derivative discretization. You have much better approaches like Range-Kutta methods or Crank-Nicolson methods, or in open form you use this backward time integration method as well. Okay.
What is the point of this then, if we just get the same result as the finite difference method?
The point is that this was just a simple example. You get the same result if you have very simple grid points. So if you have uniform grid, then you get the same result. If you don't have a uniform grid, then finite difference method is useless. You need to do this in this way, and it gets more complicated soon. Any other questions at this point? So let's look at this more in detail. So what is the Gauss theorem? Gauss theorem is generalization of integration. and it's a mathematical theory. Probably you have used it on the mathematics courses during the first or second year in bachelor's. But it's a way to convert volume integrals to surface integrals. And so formally you have terms like this, where you have derivatives or nabla dot vector. We always have these terms in convection diffusion equation. So both on the convection side and on the diffusion side, you can always write it in this form. And if you integrate this kind of terms over a volume integral, you can convert it to a surface integral like this, that this nabla is, the gradient is dropping out, and all that you have is a surface integral over the surface of, let's say, a cube over here. So in CFD and in 1D, this was just the integration law, like I discussed already. In 1D, this was just that you have df dx, you integrate over interval, and it depends only on the value of the function itself into endpoints. Same story extended to 2D and 3D. So in CFD, convection terms, those are always of this form. So in 2D, you can always write this transport term. You have velocity and then some transported quantity like temperature, scalar, species, concentration, and it's always of this form. Nabla dot velocity times the term. So that's the transport term. Something is transported by the velocity. And you can use Gauss theorem, and it boils down to something that looks like this. So the nabla is kind of like just disappeared. And in the end, this is about conservation of momentum or conservation of something. And so you have a volume, something is leaving from the volume, something is entering. And what this term is telling you is that what is the total balance. So it basically takes all the terms, like how much is leaving from here at the given time step, how much is from here, how much is entering from here and here. And when you sum those together, you get the total effect, how much this quantity is going to be changing inside a control volume during a time step. In the same way, if you have the diffusion terms, also those are of the divergence form. So this term is always of this form. And if you don't understand why, you have to go to the previous slides, last week's slides, and there these terms are elaborated. And you can do it by pen and paper to simply understand what this means. And when you kind of use Gauss theorem on that, the first divergence is dropping out, and all that you have is left is gradients on the surfaces. So those are the diffusive fluxes. So we go from volumetric divergence terms to flux form. So flux form. This is a flux form because we have normal vector of the surface. So this is an important quantity, the normal vector, and then the phase area is ds. So ds is essentially related to the area of the differential area of the cell. And in finite volume method, you can have arbitrary polyhedra, arbitrary shaped elements, and by computers you apply the Gauss theorem and calculate the fluxes, and it gets much more complicated than this when you have complex cells and stretched grids, but the main idea is over here. Integrate over volume, apply Gauss theorem, you change volume integrals to surface integrals, and that's it. So how in practice you have the mathematical side, and when you go to numerics, you have to estimate those surface integrals using sums. So you need to, so basically these integrals are summations over the phases, and these velocities, this velocity over here is interpolant of velocity on the phases. This quantity over here is interpolant of the quantity on the phases. You have a phase normal vector and the phase area, which is a discrete quantity. For example, delta x times delta y to get a certain area. And same story holds for the other terms. So you have the analytical side, that's mathematics, and then this part, which is numerics. You go from integrals to summations. And this is very important, that will be discussed in some of the homeworks, that how you do the interpolation. Do you use central difference or linear interpolation to do the interpolants, or do you use some other like flux limiter, upwind methods? So you can have different approaches to do the flux calculations, linear, upwind, or you can have a flux limiter. But and the purpose of these options B and C are that numerical methods can become unstable. So you can start getting these small wiggles in your solution, and when time goes on, those explode, sometimes very quickly, exponentially. And the purpose of these options B and C is that you need to, in practice, stabilize your simulations just a little bit, as little as possible, but just a little bit. So you often need a little bit numerical diffusion to stabilize the solution. And then how does OpenFOAM user see the finite volume method? How do you see it in practice? So you have different dictionaries. I hope it is still called FB schemes. Some time ago, I think they may have changed. But anyways, the main idea is here. You have a dictionary in the input files, and there you have to define what is your DDT scheme. So you have to give time, specify OpenFOAM how you discretize the time derivative. If you have gradient schemes, how do you calculate, for example, pressure gradient? Okay, here it's telling that it uses a Gauss theorem and linear interpolation. That would be the best. I mean, optimally one would always use linear, but practice can be not non-optimal sometimes. And here it's telling that the default value is Gauss linear. So whenever OpenFOAM calculates gradient of some quantity, this is telling that use Gauss linear. And if you have divergence terms, like you have in the convection terms and the diffusion terms, here it is telling that use, for example, in the momentum equation, this is the momentum equation convection term, use Gauss linear. And then here you could specify different. You could say Gauss upwind, or limited linear or gamma v or something. And then how do you know all the options that you have? You have maybe 100 different keywords that you could write over here. If you write there Gauss, let's say banana or some nonsensical word, then and start the simulation, it will stop and tell that, okay, there is no such keyword as banana, but here is the list of all the keywords that you can put over here. So it will tell you you will find out all the options in this way. Or you can look at the OpenFOAM user manual, find different options. Here is a piece of OpenFOAM code. So in OpenFOAM, you use different solvers. I think that you have now used possibly something called PimpleFOAM when you did the lead-driven cavity. And there is a small piece of so-called top-level code where you kind of which is the solver. That's kind of like the main for loop or main while loop of your simulation. So you have a time loop over the time steps, and inside that time loop, OpenFOAM top-level solver, let's say, I think there is a solver called PimpleFOAM still today. The top-level solver, it's a small piece of code, maybe 100 lines. And if you look at the source code, there you specify the governing equations. So for example, momentum equation, Navier-Stokes equation is marked over here. And you see how OpenFOAM syntax works. You have Navier-Stokes equation has a time derivative of velocity. Okay, you can probably deduce that this is there's a connection, quite obvious connection with the Navier-Stokes equation. So we have in Navier-Stokes equation the time derivative. Then there is a convection term. This is maybe a little bit less obvious, but that term is commonly seen in OpenFOAM. And over here, same term. And what else you have? This term is probably having something to do with that one. And pressure gradient, okay, then it becomes a little bit less obvious, but you have pressure gradient, negative pressure gradient over here as well. And then you have something else which I don't go into, but MRF is referring to moving reference frame. So if you have moving parts, let's say a propeller or a wind, let's say a wind turbine blade or some other like a pump or something where some part is moving, then you have to take into account the motion of the boundary as well, and that term may do the job in those cases. But normally we don't have that kind of situation. Okay. Now I've been discussing about finite volume method. I showed some MATLAB examples. Maybe I could conclude still one more thing. So indeed, in general, average of a function over the volume V is defined like that. So you integrate over the volume and divide with the volume. So that was the basic idea of finite volume method. You you have some quantities. Let's say in this example, it could be concentration of moisture, cloud aerosols. Velocity is the velocity of the airflow. And we have the governing equations. So you have transport equation for aerosol concentration in the cloud, water, let's say water vapor, water aerosol concentration. You have Navier-Stokes equation for momentum. So if you have them in differential form, they look like this. But if you volume average over the differential form, so you volume average, this term is the same, integrate them over the small volume, divide with the volume, do it term by term, like that. And then you can convert those volume integrals into surface integrals. So now we have actually converted all these volume integrals into surface integrals. So here they are volume integrals. And you see, for example, over here we have this nabla dot something. But if you go over here, this nabla dot something has disappeared. So that's, just a derivative rule. You derivate over an interval, you pull out the derivative, and it just depends on the values of the function in the endpoints. So here, these have become surface integrals, and we utilize the Gauss theorem in this form. And how this goes to practice is that you have to estimate these numerically somehow. So these surface integrals are converted to summations, and then you need to estimate these numbers as interpolants on the cell faces. And you can have explicit methods, and in these explicit methods you know these directly. So please note that you have this n is over here and here as well. So that n is referring to the previous time step. So in explicit method, you would estimate this directly, knowing the existing value of the solution from the previous time step, the current value that you have. But in implicit methods, you do something else. You can linearize this a bit differently. So you can also take that, you say that, okay, this term is from the previous time step, but this term, you can say that, okay, that's unknown. That would be actually the solution that you want to solve for the next time step. And in that case, these equations would lead to a linear system, ax equals b, where the x is now the velocity, the next time step, next time level that you want to solve. And next lecture, we will discuss this point a bit further. I'm talking about a lot of things, and starting from here and going all around, but it all revolves around the same topics. What is the finite volume method? What is a numerical method? How do we discretize equations? And then in some cases, we need to solve linear systems of equations. And actually, linear systems of equations, ax equals b, is what OpenFOAM is solving to you on every single time step. So many times during one simulation, you're solving linear equations for velocity components and for pressure field. And this is done many times, and that gives you the numerical solution of for example, a lead-driven cavity that you have already returned, I think, for the first round. But that's all I had to say today. The second lecture is out already. Second homework, I mean. And next week I will talk about matrices and AX equals to B. And we will be doing MATLAB, I think, in next lecture, so that I will give out and release the final assignment, and we start solving the final assignment during next lecture. So I actually recommend that you download and install MATLAB on your computer, or make sure that you can access some computer class to open MATLAB via SSH.
Question on that. Is the MATLAB online good enough for this? Have you tried? I have. It's a little bit different, and not all things work same.
What is MATLAB online?
It runs MATLAB through browser in some of their servers.
I think that should work. These are not heavy simulations. This should work. Yeah.
I had a question regarding the, let's say, OpenFOAM and tool that we are using. My question is that what is the advantage of this OpenFOAM over, for example, other CFD tools with graphical user interface like COMSOL, ANSYS, or any other tool? So what is the competitive advantage for OpenFOAM?
Well, first of all, I think it's a good question. I think that first of all, like the number of users, I think is speaking for itself. OpenFOAM is has the second most users worldwide nowadays, as in a CFD code. I think ANSYS Fluent, the commercial code is like has the largest number of users. But OpenFOAM is the largest, so I think that number speaks for itself. It's over 100,000, perhaps even 200,000 downloads when a new release comes out. So large user community. And the second thing is that finite volume methods are the method to solve fluid mechanical problems. Whenever you have complex geometries or more complex meshes or turbulent flow in particular, finite volume method is the way to go in any engineering approaches. Okay, you can do it with other methods as well. That's possible. Everything is possible. But finite volume method is, we have conservation laws, and it's particularly easy to simulate conservation laws, conserve something with the finite volume method. And the reason for this is that we have the Gauss theorem, and that's kind of related to these conservation laws as well. So I would say, just long story short, it's a compact method to solve conservation laws, and this conservation property is kind of built in to the method quite naturally. But you can build it in finite element methods, but things are much more complicated in that way, in my opinion.
All right. Yeah. Thanks.
You can solve fluid mechanical problems with especially laminar flows with COMSOL or LMR or some other codes. But usually these finite elements, they work best for laminar flows. But when you go to turbulence or anything that's a bit more complex, you have great benefit and advantages in finite volume method. Any other questions? Finite elements, COMSOL and Elemer and these codes, you would typically use a lot in solid mechanics problems. That's most common application for them. But you could also apply finite volumes in solid mechanics problems, but it's not very seldom seen. So
wondering, expanding on that, like combination of solid mechanics and fluid mechanics, like interaction of solid mechanics and fluid mechanics, how would that go?
Yeah, that's a problem type called fluid structure interaction. So, for example, you could have some vibrating surface in a fluid, like a vibrating propeller. There you would have two ways to go. One approach is that this, I think, can be done in open form, but some people have done it also so that they couple two codes, so that you can take, let's say, finite element code to solve for the solid phase vibrations, and open form to solve for the fluid motion. It's a very complicated problem type for many reasons. You have very high frequencies typically, and large, let's say, large scale separation between the frequencies in the flow. If you have turbulent flow in the propeller, outside the propeller, and then you have the vibrations in the solid, it's very challenging problem to solve.
Thank you.
But one interesting approach is also you can in general have moving bodies. So, for example, if people have simulated a small fly, a mosquito with the little wings or butterfly with the wings flapping, and this has been done in open form, and there are as many methods as there are people how you can solve these. So there is only imagination is the limit. That for example, people have simulated with so-called immersed boundary methods. You can immerse the mesh in the solid part in a fluid mechanical grid. And what people have done already in the 70s is that they simulated how a human heart is pumping blood and the motion of the elastic body, how that's interacting with the fluid. So already in the 70s this has been done, but of course with very coarse grid resolution. But that can be done nowadays as well. And I think same group who did that in the 70s, they have simulated if somebody jumps out from airplane with the parachute, and then how the parachute opens and how it's interacting with the fluid. So even that can be simulated with computers nowadays. It's very complicated problem. You have very thin fabric that's opening, like silk or something, and how it's opening and how it's stretching and interacting and moving with the wind, and quite complex physics. Anything else? Okay, thank you for your attention, and let's get back next week.
Yeah.
Nice week.
Thank you. Bye.
Bye-bye.
Thank you. Bye.
Bye. Thank you.